Okay, so in this problem, we're looking at centripetal forces. We're looking at a simple approach here of just kind of using friction to go around a turn right here. And let's take a look at the problem we've got. This is 6.5, problem C3, number 9.11. You've just obtained your driver's license, and whoop, 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 whoop. Oh no, it's the red and blue. You've been pulled over by the popo. The officer states that they clocked you going 45 miles per hour around the bend. And you're sitting there like, I wasn't going 45. So you show up to your hearing, magistrate, judge, whatever, and you claim, because you're a great physicist, you claim that the officer is incorrect. And not only that, but you can prove it. You can prove it. You can prove that it would be impossible for you to travel at 45 miles per hour with the curve, the level curve, the flat road, having a radius of 32 meters, assuming that the coefficient of friction between the car's tire and the road is 0.8. So you do this by proving the actual top speed at which a person can drive successfully around the curve. So that's, you don't slide out of control and crash into a tree. What is the actual max speed that you could travel around a curve? And sometimes you see a curve around PA, and it's like, take it slow, 20 miles per hour. Like, those signs are there for a reason, people. So let's actually calculate what is the max speed you could take a curve if it had a radius of 32 meters per second. Now, the most important thing you could do in every problem ever, old Grandpappy Botzer said, draw a picture. So we're actually going to draw two pictures here. We're going to draw one from the top down first, okay? So this is a top down, or like a bird's eye view. I don't know why I just wrote birds, but it's a bird's eye because it's like looking down on you. So in this curve right here, you've got some road, and the road isn't circular, but we're driving on the curve, or we're driving over here. And our car has a linear velocity going forward, but there is some force acting on it towards the center of the curve such that it is the centripetal force. Okay, so there is some force acting towards the center here, and it's causing our car to make this left because that's what we did on the road. Now, if we look at another picture, we'll draw a picture from behind the car. Okay, so here's the road. Here's our car moving forward. We need to ask ourselves the question, what is actually causing our car to turn to the left? Because we already know that, yes, because this is a level road, there's a weight, which equals mg, and there's a normal, which we know will also equal mg because this is a level road. It's not an inclined plane, so the normal and weight will be the same. But what is actually causing our car to turn to the left? We know whatever that force will be, it will become the centripetal force. But what is that force? Well, we all live, maybe we've seen or live around a snowy climate. And in the wintertime, as we're driving down the roads, you might hit some ice on the road. And if you try to turn on the ice, it's not going to work well. You're just going to keep going straight, and you're probably just going to crash into something in front of you. So we know that if ice has very little friction on it, that it is the friction that is actually allowing our cars to make a turn. So this force acting to the left here, this is friction, which we know friction is fun. Friction is mu multiplied by n, the normal force, which we have. Yoink. So we know that this friction is fun here, which means that since this is the only force acting on our car in that left, right, or into the circle, out of the circle pathing, I can make friction our centripetal force. Okay, so if we set up this equation, we know just generally, F equals ma. And in our case here, because we're going in a circular motion, or we're making a turn around a circle, we can say that the centripetal force equals the mass multiplied by the centripetal acceleration. And that's just because we are doing a turning thing here. So normally just say F equals ma, but because we're turning, we're rotating, we need centripetal values here. And do remember that this centripetal force, it could be the sum of many forces. There could be more than one force here. We'll actually see that definitely in our next examples with roller coasters going through loops or running over to Chick-fil-A to grab one of those sandwiches. But in our case here, the only force causing us to act inward on this circle is this friction here. So when we write out this equation, all we have is friction, because that is our centripetal force here, equals a mass multiplied by a centripetal acceleration. If we expand the friction equation and the centripetal acceleration equation, well, we know that friction is fun, so there's mu times n. And we know the centripetal acceleration is v squared over r. Expanding this further, we know that the normal force is equal to mg. And this is actually really cool because if you go back and you look at the problem, we don't actually know the mass of the car. We don't know if it is a small little, sporty sedan, or we don't know if it's a big truck. But it turns out it doesn't matter. When we start writing this out, mu times m times g equals m v squared over r, multiplied, we quickly see that the masses being on both sides of the equation, they divide each other out. They've canceled. So it doesn't matter the mass of your vehicle. All that matters is what is the coefficient of the road? What is gravity, which we're here on Earth, it's 9.8. What is the radius of the road, or the radius of that circular bend, because we are going to multiply each side by r so that these r's go away. And what we quickly have is that v squared equals rug, r mu g. And then if we want to get rid of the square, we'll simply take the square root. So our final answer comes out to be that the velocity is equal to the square root of the radius of our curve, 32 meters, times the coefficient of friction, 0.8, times gravity, 9.8 meters per second squared. Our units on the inside are actually meters squared per second squared, which works out really well because when we take the square root of that, we get meters per second. And if we pull up our little calculadoro and multiply this, 32 times 0.8 times 9.8 equals 250, 0.88. And when we take the square root of that, we simply get 15.84 meters per second, which if you just throw that into like a Google converter or whatever to miles per hour, it's approximately 35 miles per hour. So if that officer said, hey, you were going 45, well, if you were going anything faster than 35, your car would have slid out of control and you'd be into a tree. And because that didn't happen, you might not have been going 45. You probably weren't going faster than 35, or else you would be out of control. So that's just a cool little example there. It's our first centripetal motion problem. This problem itself is finished. In later problems, we will take this a little bit further. Our next step that we're going to do is, instead of going in horizontal circles, we're going to go in vertical circles, which are going to give us more than just one of these centripetal forces. We're going to have multiple forces adding up to be a net centripetal force. And then later on, we'll go through some banked turns and show how maybe if the turn was banked, the officer could have been correct. But until then, like I said, this problem is finished. Adios, and y'all take it easy.